Hello, I'm Louise Hewitt from Future Facilities, and today I'm going to be taking you through what a data center digital twin is and how it can be used to optimize data center operations. Let me start by asking you a quick question. Why do we build data centers? Hopefully, the answer is very obvious. Because the data center is driven by the business's needs. The business need for companies with streaming services and cloud storage services is very clear. And of course, for others, it's a case of maybe having to build their own data center for security reasons, or maybe you plan to build a data center and use it as a colo site to generate revenue. With this in mind, I think my real question is, how much value does the data center bring to the business, and how do I justify and quantify this? For most people, the way to quantify that value is how many kilowatts of capacity am I going to get from building this data center, and will it meet my current and future business needs? Sadly, most data centers actually fall short of their projected capacity, which in turn means that many operators never see the full value or full benefit of their original investment. Surveys conducted by Future Facilities and 451 found that the typical enterprise data center only uses 56% of its planned capacity. And even the hyperscalers with their homogeneous designs actually still lose 14%. So why is all this capacity and money just being wasted? Well, the answer may not be obvious, but the answer is change. When the data center was originally designed, it was most probably for uniform loads across X number of racks, based on X kilowatts of cooling capacity being available to be shared between those racks. Once the site is operational though, how many people are actually sticking to that plan? I would put money on it being none. The business's needs drive change. IT equipment changes over time, power densities become higher, and all of a sudden your perfect design is broken. Let's have a look at an example of how that happens and what factors are at play here. So in this example, we have a client that wants to install some new high density equipment. Now, depending on how old the data center is, this density of equipment may not have been considered when the data center was planned. So you may have planned for 3 or 4 kilowatts per rack, and suddenly you're being asked to install 5 or 6 kilowatts per rack in a vendor configured cabinet. Typically, there are several people involved in this process, and they're looking at everything from networking, IT, power, and cooling from the facilities team. So each of these people may use a different tool to plan their deployment. Maybe the IT team are using Visio to make placements, and the power team using Excel. There isn't a final check of all of these aspects together though, before the deployment goes live. Because of this, when the equipment is installed, our invisible enemy, airflow, takes matters into its own hands. And what we actually see is thermal alarms going off on the equipment that's located in the next row over from new deployment. So this new deployment has caused a thermal issue that wasn't foreseen. But why? Where did we go wrong? All of the teams did exactly what they needed to do and ticked off their part of the deployment. Put very simply, the management process here for the deployment lacked visibility of how the data center would react to this change. Many current management practices are disconnected from their desired performance and business outcomes. In this case, that led to the customer losing 30 kilowatts of capacity as the equipment in the row behind overheated and was then out of action. This is just an example of one deployment, one single data center change. Now imagine those happening over the whole data center lifecycle. How many times will the team end up fragmenting the design, space, power and cooling, resulting in lost capacity and value for the data centre. Quite often, I'd imagine. So now let's have a look at how this could be made more efficient operationally using the digital twin. If you haven't heard of a digital twin before, to put it very simply, a digital twin is a virtual replica of a physical asset, in this case the data centre. A digital twin should be made up of two parts, live data and simulated data, so that you know where you have been and where you are now, but more importantly you have the ability to predict where you're going next. Remember, that was the missing ingredient in the last deployment. For data centres, the live data part can come in the form of monitoring points, say pressure, temperature and airflow, which may be part of a DCIM solution, for example. And the simulation part can be provided by a tool such as Future Facilities Six Sigma DCX Suite. To give you a sense of what a digital twin actually looks like, we can walk through one now, alongside its real-world counterpart. You can see that the digital twin is not only made up of the architectural aspects of the data centre, but also its power connectivity, its IT assets and their placement in space, its cooling infrastructure, and also its logical network connectivity. At the very finest level of detail, components like an individual blade server can be represented both visually and operationally as individual assets, like you can see here. On the surface, this digital twin may look like a DCIM tool, but what makes this digital twin completely unique is its built-in physics-based simulation capability that mimics the physical behaviour of its real-world counterpart, including the airflow performance. But why is that so important? You may remember that the piecemeal approach of deployment previously, with no visibility of how changes will impact the data centre, led to thermal issues. So surely being able to visualise the airflow alongside all of the other deployment attributes is key to good operational deployment. So let's go back to our original case study and let's see how this joined up approach to deployment using the digital twin, including simulation, can affect the outcome. The digital twin brings together each of those previously siloed teams within a virtual world that's made up of two parts. The 3D model that represents every physical object and their placement in the data centre, and a physics-based simulation capability that enables the digital twin to mimic the physical behaviour of the real data centre. So this IT deployment can be initiated through a DCIM tool, which feeds into the digital twin, or it can be a direct input into the digital twin, depending on what the client is already using and what workflow they prefer. In this case, we'll deploy our racks using a direct input of the digital twin. So once this request is made, the digital versions of the IT hardware to be deployed are selected from a virtual library. This virtual IT hardware contains the same attributes as its physical counterpart. The IT or the rack is placed within the digital twin in the desired location and use slot. Each of those previously siloed teams now goes about planning this deployment in more detail, within the same tool, the digital twin. For example, the networking team allocates ports to the server. The power team makes the logical connections from the servers all the way up to the utility. And the facilities team look at cooling and weight availability in the selected area that's been chosen for deployment. Once all of these virtual components are installed, the facilities team can run a simulation to check airflow availability. By running the simulation, the digital twin predicts that there will be thermal issues in the row behind. So these are the thermal alarms that we saw in the start of the presentation. This puts other business critical IT at risk, and the facilities team decides that this deployment can't go ahead as it is. You can see from the simulation that the hot air from the new IT is being pulled straight into the inlets of the existing IT behind. But all is not lost. Because all of this has already been done in a virtual environment prior to physical implementation, they now have a chance to salvage the situation. The team decides to move the IT to an area where they believe they have better cooling capacity. Networking, IT and power engineers all agree that this location is also suitable for them, and they go about updating their virtual plans within the digital twin. The facilities team once again run a simulation, and this time they can see that there are some virtual alarms going off, but this time they're for power, not airflow. As we can see, the airflow is ample and all of the racks are receiving enough cooled air. When implementing these virtual plans, the power team ran a virtual failure of part of the power system to make sure that the IT had the redundancy required. And sadly, it did not. So this deployment is actually now being limited by power instead of being limited by airflow. The facilities team decide that the only suitable place for the IT is back in the original location, but they change out the floor grills and decide to add an additional cooling unit to deal with the airflow issues previously seen. They can do a cost-benefit analysis here before investing in the new infrastructure to see whether or not these additional cooling units are really worth the money. But the addition of the cooling units in this case works. We can see that there are no thermal alarms and all of the racks are receiving ample cooling airflow. But the team does notice that they are now over-provisioning this airflow, and therefore they're wasting money and energy. So they decide to run one more quick simulation to see if they can reduce this. Using the simulation, they are successfully able to reduce the wasted airflow and remove the additional cooling unit that they placed earlier, resulting in energy and money savings that they wouldn't have had if they hadn't have simulated first. They've also recovered that 30 kilowatts of capacity that would have originally been lost if they'd have installed without simulating it in the digital twin first. By working together in a single platform, this team have a solid plan to deploy the physical IT that they are happy with, and everyone feels confident that they have minimised risk and made the deployment as energy efficient as possible and protected the availability of the new IT as well as that of the already existing IT. It's clear that the digital twin methodology has helped in not only making the right decision when planning, but also in helping the team to communicate to find the best possible solution. In this case, that saved a potential loss of 30 kilowatts of capacity. So this example has shown the benefit of the digital twin for one decision. However, as I mentioned earlier, there are thousands of decisions and changes over the span of the data centre's life. So the key to making sure that you realise the true value of your data centre so that it meets your business needs is to make every decision using the visibility that the digital twin provides, so that you know that you're working as efficiently and as confidently as possible. Working in the virtual environment will maximise efficiency, resilience and capacity whilst reducing risk, and ultimately that will lead to cost savings too. Thanks for listening to this presentation. I hope you found it useful. If you are interested to learn more about the digital twin or how it can be used, please don't hesitate to reach out to me after this session. And please also do ask me questions through the platform. Thank you for your time.